No, I don't think I'll study for my chem test. I think I'll play with my Rubik's Cube. Okay, let's get started. Oh no! Howdy, young'un. Let me help you with that there problem. But who? No time for questions, son. Let's move along. But where are we? Didn't he say he was gonna help me? Guess I'll just have to find my way out of here. Whoa, what's this?
We're the octet and we rule because of the octet rule.
What? What the heck is going on?
We're the octet. We're perfectly happy the way we are. We're the perfect configuration.
How so?
You see, when there's 8 of us, we attain the status of a noble gas configuration. Once we achieve that configuration, we won't let anybody into our clique. We'll go to any measure to have a perfect configuration, and sometimes we have to kidnap other electrons or donate some of ours to reach that goal. When we donate or accept, we become an ion.
Sounds like you guys are perfectly happy the way you are. I'm gonna leave you be. Hey, what are you two doing?
Well, hello there. Meow. My name is Cat Ion. Meow. Want some electrons? Meow. Well, they're free. I love giving things away. Meow. But my sister Anne here loves taking things. Gimme. I love taking everything. Gimme.
So you guys work together?
Of course, you could always find us together in ionic compounds like NaCl or Kf.
When we form bonds between a metal and a nonmetal, there is almost always transfer of electrons. These type of bonds are named after us and are called ionic bonds.
Ionic compounds are materials that are held together by ionic bonds, like table salt. Typically, ionic compounds are very hard, have a high melting point, and do not conduct electricity unless they are in aqueous solutions or molten.
Fascinating. Of course, ionic bonds can't be the only bonds out there.
Well, of course not. There's also metallic bonds,
which are how many metals are held together, like a sheet of copper. The electrons flow more or less freely across the substance, making it commonly referred to as the sea of electrons.
Electrons! Ah!
The sea of electrons makes the metal conductive to electricity and allows for many of the properties of metal, like malleability and ductility.
There are also covalent bonds, which have nothing to do with oceans or water or anything wet. Covalent bonds are sort of like ionic bonds, only where ionic bonds imply the taking of electrons, covalent bonds share electrons.
They only occur between nonmetals and can feature a double bond or a triple bond. If you look here, oxygen has a double bond, and cyanic acid has a triple bond.
Covalent bonds are pretty sick.
But not as cool as ionic bonds.
Well,
I'd better get out of here before this turns ugly.
Evil Incorporated.
Like riding this Incorporated with this shoe. Soon, smelly shoes will be gone forever.
What are you doing?
What? I'm creating hybrids, boy.
Hybrids? Like Toyotas?
No, silly child. The Prius is for women. I'm talking about real hybrids, like hybrid orbitals, you know?
Hybrid orbitals?
Okay, let me give you the backstory. You see, back when I lived in Germany, my father explained hybridization theory to me. He said, it occurs when several atomic orbitals mix to form the same number of equivalent hybrid orbitals. To which I promptly responded, well, what a terrible, unclear textbook definition. And then he kicked me out of Germany.
And then I spent the rest of my life trying to figure out what hybridization was. Well, let me just explain it to you this way. Well, basically, in just about every bond in the universe, hybridization occurs to allow bonding to occur with more simplicity. For example, here is a fancy diagram of methane, CH4. Now, instead of using two s orbitals and two p orbitals to bond, the carbon combines all of its orbitals into four sp3 orbitals, which extend farther into space and allow for easier bonding with the hydrogens. Now, I'm going to stop right there because we only have about 10 to 15 minutes for this project, but if you're confused, just look at page 234 and 235 in your textbook if you want more information. Oh, before I go, I want to show you one more thing. How simple covalently bonded molecules get their shapes. Well, if you look right here, here are some diagrams of molecular shapes. Now, because of the Vesper theory, which stands for valence shell electron pair repulsion, lone pairs of electrons influence the shape of a molecule. Well, like this one, which has a lone pair right here. Oh, I probably shouldn't be writing in my textbook, but you get the idea.
Wow, that was really confusing.
Yeah, well, that's chem. And we haven't even gotten to thermochemistry yet. Well, like I said, you can look at page 234, 235, the 230 range of your textbook. And that'll give you some more information.
Okay, well, good luck with your hybrid thingy.
Give me that! I want it more!
What the heck are you two doing?
We're exploring intramolecular forces.
Namely electronegativities.
What?
I'm being two hydrogen atoms.
And I'm being an oxygen atom.
But together we're being water!
You see, water is what we call a polar covalent molecule.
Even though the molecule is covalent, and we technically share the electrons, the oxygen atom is more electronegative than the hydrogen atom, so it hogs the electrons.
These types of bonds are called polar covalent bonds.
Compounds with polar covalent bonds are known as molecular substances. They typically have low melting and boiling points and are usually soft solids. When dissolved in water, they are usually non-electrolytes. While we're on the topic of bonds, let's go over bond dissociation energy.
Basically, BDE is the amount of energy it takes to break apart a bond. Usually it's expressed in kilojoules.
For example, the BDE of water is about 917.8 kilojoules.
Hold it right there, partner.
Oh, no!
What?
Now, I ain't here to kill you. I'm here to talk about hydrocarbons. You remember that big thing on the test?
Oh, yeah. Now, let's start with the basics. You can characterize a hydrocarbon very simply by giving it a prefix which denotes the number of carbon atoms that are in it. For example, meth is 1 carbon, eth is 2 carbons, prop is 3 carbons, bute is 4 carbons, and then the rest are all their regular prefixes like pent, hex, sept, etc. Now let's take a look at what they gave us in the book. Right here are all sorts of different ways for writing out the formulas for hydrocarbons. Starting up at the very top, we have its molecular formula. Then, going down, we have its complete structural formula. And then, as we get down the list, basically everything gets simpler and simpler until we get all the way here, which is the line angle formula. So basically, we have the 3 most common ones, which are structural, condensed, and molecular formulas. Alright, now let's talk about unsaturated hydrocarbons. So far, all the hydrocarbons that we've seen have only had single bonds. Now, once you get into unsaturated hydrocarbons, you can have multiple carbon-carbon bonds, such as the ones here, which have double bonds, and then this one all the way up here, which has a triple bond. Now, the ones with single bonds are called alkanes. The ones with double bonds are called alkenes. And the ones with triple bonds are called alkynes. Now on to isomers. there are two types of isomers, structural isomers and geometric isomers. Right here we have examples of structural isomers, basically meaning that they have the same molecular formula, but as you can see here, this one has a CH3 coming out of the middle and this one doesn't. So they have a different structure. Now over here we have some geometric isomers that, like the structural isomers, have the same molecular formula, but what makes them geometric isomers is the fact that these parts are oriented differently around the double bond. So here we have what is called a cis configuration, and up here we have a trans configuration. While we're on the topic, let's talk resonance. Basically, resonance is whenever you have a compound where you draw the electron dot structure like these two, but you can express it in more than one way. So like you see right here, we have the 4 dots making the double bond in this part of the ozone, and over here we have it in this part of the ozone. Basically, these two are considered resonance structures. Okay, we're almost done. So right now we're going to talk about the difference between cyclic, saturated, unsaturated, and aromatic compounds. Now we already talked about saturated and unsaturated. In case you don't remember, saturated is when there's only single bonds, and unsaturated is when double or triple bonds exist in the molecule. But stuff here where we have all the carbons connected in a sort of ring shape are called cyclic hydrocarbons. And adding on to that, anything that has a benzene on it, which would be something like one of these, is considered an aromatic compound. Finally, let's talk functional groups. Basically, a functional group is an arrangement in an organic compound that makes the compound likely to take part in certain reactions. Well, the only 4 that you really need to know are alcohol, ether, carboxylic acid, and ester. Now, if you look at page 726 in your textbook, there's a lot more information on the topic. And pretty much that's all you need to know to go out there and ace that test. Now, go get 'em, Tiger. Sweet! Now, how do I get out of here? Right over there, sport. Gee, thanks! Oh, he's gone. Well, guess I better find out where that door leads.